Hello everyone, today we'll be covering the lesson Group 2 in CAIE A-Level Chemistry. This is a part of the AS syllabus and there's not much to it. The only thing within this topic is just some basic reactions and the observations when this reaction happens and some basic trends down the group. So the first thing that I need to say to everyone is down the group for Group 2, and this is just properties, I'm not talking about any trends. So down the group, the atomic radius increases, and we all know why. It's because more shells are added, like more number of principal quantum shells, so that's why the atomic radius is higher. There's more to it, but that is the simplest reasoning. The ionization energy decreases. The first ionization energy decreases, and that is because more shielding effect and increased distance between valence electron and nucleus. And the third is reducing the reducing power increases. So from your IGCSE years, we'll get more into this in another topic in AS, but from your IGCSE years, you know that reducing means, well, when something gets reduced, it gains electrons, if you remember from oil rig, right? Oxidation is loss of electrons and reduction is gain of electrons. So when something is reduced, it gains electrons. However, when something is a reducing agent, it reduces something else, so it undergoes oxidation itself. The reason why a reducing power increases down the group, and recall that oxidation is a loss of electrons, is because down the group, the ionization energy for the group 2 elements, it decreases. So this corresponds to this. Sorry, it's the other way around. This corresponds to this. Okay. Now that is just some basic properties of group 2 elements. Okay. And I have to erase that. Just give me a minute. Okay, there. Next up, we have reaction with oxygen. Plus the observations. The observations are rarely asked, however, it is better to know because they can even ask it in A2. So the first reaction is, okay, well, before everything, let's just list out the common group 2 elements. So we have beryllium, we have magnesium, we have calcium, then we have strontium, and then we have barium. We don't usually include radium in the list of group 2 elements in our syllabus. We only talk about primarily these four, sometimes this. Okay. Anyway, so the reaction with magnesium with oxygen gives magnesium oxide. I'm not balancing these equations, but if you were to balance it, you just add a half here, or add a 2 here and add a 2 on this side. Like add a 2 here or 2 on this side. Yeah. And then the reaction is same down the group. So calcium plus oxygen would give you calcium oxide. Strontium plus oxygen would give you strontium oxide. And barium plus oxygen would give you barium oxide. The reason why there's only one O is because this has a +2 oxidation state and this has a -2 oxidation state. So one of each is required to form an ionic compound or an ionic salt. Now this is well and easy. I'm sure that if you were to get this equation, you'd be able to guess it. But now the observations are important. Observations are important. Okay, so with magnesium, whenever oxygen reacts, a bright white flame is observed. Whenever there's a reaction with calcium, a brick red flame is observed. And for strontium, if I'm not mistaken, it's somewhat red or scarlet. And for barium, it's apple green. Now it's not perfectly green, but it's somewhat apple-like. If you've ever seen a green apple, that's basically what the color of that's basically the color that's observed when pure barium is reacted with oxygen. Okay, so these are the observations, and this is the reaction. It's recommended that you note this down. Anyway, next we'll move on to some reactions, like the trend in reactivity down the group. So, down group trends, right? So the first thing is that the reactivity in general of group 2 metals increases down the group. There's an E here, okay? So it increases down to group 2 metals. And the reason why this is because, well, the reactions occur mainly because of reduction and gaining of electrons, like for instance, magnesium plus oxygen, yeah, and calcium plus oxygen. Now, the reaction with calcium and oxygen will take place faster than the reaction between magnesium and oxygen. And the reason is because the ionization energy of magnesium is lesser, right? And therefore, it donates electron much more readily to the oxygen molecule. And therefore, the reaction is much faster. It requires less energy for this reaction to take place. Whereas for magnesium, it just takes more energy. So that's the main reason for the group 2 metals have like, increasing reactivity down the group. And the same goes for the reason why the reactivity of magnesium, sorry, not reactivity of group 2 metals with water increases down the group. So yeah, that is an example of reaction. And an important reaction that we learned also in chemical periodicity is the reaction of magnesium with water. So when you react magnesium with cold water, you get magnesium hydroxide plus hydrogen gas, right? But when you react it with steam, H2O, where this is steam, you get magnesium oxide instead. Okay, so this is with cold water, and this is with steam, and this is important. And it was mentioned in the last lesson. And a small miscellaneous fact, and that is BeO, beryllium oxide, is amphoteric, similar to Al2O3. It's an amphoteric oxide, so just remember that. It's not that important, but what's the harm in remembering it? Anyway, let's move on to the next part of the lesson, which is trends. Trends in thermal decomposition and solubility. So let's first talk about thermal decomposition. In your syllabus for thermal decomposition of group 2 with their respective anions, there's only 2. So there's for group 2 carbonates and group 2 nitrates, NO3, 2. And the reason why there's 2 here is because NO3 is minus and the metal has an oxidation state of 2, and therefore there's 2 anions required. So the thermal decomposition equation for thermal decomposition reaction for carbonates gives off the oxide of the metal plus carbon dioxide. That's what it gives off. So for instance, magnesium carbonate, right, upon thermal decomposition would give off magnesium oxide plus carbon dioxide. Same with calcium, CO3, when thermal decomposition takes place, CaO plus carbon dioxide. Okay, that's what's given off. And the observations for this reaction would be a white solid remains, and because this is gaseous form, effervescence, right? That's what's observed. And Well, that's pretty much it about thermal decomposition, about group 2 carbonates. There's not much to it. And the thermal stability we'll talk about next. And the other thing is the thermal, okay, wait, I'll just move down. The other thing is the thermal decomposition of group 2 nitrates. So XNO3 2 would decompose to give the oxide plus nitrogen dioxide plus oxygen. Now, I suggest you remember like the balanced form of this because they normally require the balanced form, and it's a bit time consuming to balance long equations like this in the middle of your paper when you could be investing time elsewhere. So the balanced form for this equation is 2, 2, 4, and this is left as 1. Okay, and because there's 1, I'm not writing a 1. So for instance, magnesium, again, we'll take that as an example. Magnesium nitrate. So 2 magnesium nitrate would decompose to form magnesium oxide plus nitrogen dioxide plus O2. That's what would form. And what you would observe for this reaction is, well, there's a white solid that remains. There's a colorless gas, but because something else is formed, you don't normally observe that colorless gas. And the other thing that's formed is nitrogen dioxide, which is a brown gas, or you could even say fume, depending on the conditions. So this is the observation that's there when the decomposition happens. And one thing that's important that I needed to mention, but I forgot to, but it just came to me. Whenever you're writing thermal decomposition reactions, yes, the compound is burning, sorry, not burning, but breaking down due to heat, but you don't, like, there's nothing added on the reactant side. It just simply breaks down due to heat. So you see, over here, there's nothing added to the reactant side. However, it still breaks down, and that is because of heat. The compound, like, for instance, magnesium nitrate here, it does not really react with anything to break down to magnesium oxide. It just, like, breaks down due to the application of thermal energy. I hope that makes sense. Anyway, that is it for the trends. No, not the trends, sorry, the reactions themselves. And now we'll get into, okay, why does it show this? Okay, what else? Okay, now we'll get into the trends. Okay, and there's the trends that you need to know are down the group for down group 2, so down group 2, the thermal stability. Okay, wait, this is important, so I'll just give an asterisk. Thermal stability, or thermostability if you want to make it short. The thermal stability of sulfates, nitrates, or carbonates increases. And what this means is that the temperature required to break it down thermally T required what? Right, the T required increases down the group. Okay, this is important. The thermal stability decreases down the group for all these anions, the compounds, which in a sense means that the temperature required to break them down increases down the group. And the reason isn't important right now, but it's something that you get into in your A2, in the A2 part of the syllabus. And it has something to do with something called the lattice energy, which I won't get into now, but this, if you haven't checked out my previous videos, I do suggest you check it out. But when we talked about bondings, we mentioned that not like almost every bond is neither purely covalent nor purely ionic. And even in case of, so 2 plus and CO3 2 minus, in case of this, there's a distortion that happens. Like there's this is a perfect circle, assuming, and because of this attraction, there's a distortion in the shape of the anion. But we won't get into it now. This phenomenon is called polarization or distortion, and it has something to do with the lattice energy. But anyway, we won't get into it now, so let's just ignore it for now. Okay. All you have to do is accept that down the group for the down group 2, the thermal stability of sulfates, nitrates, and carbonates increases. Okay. Another thing is the solubility. Oh, I forgot to add in also hydroxides. So for every anion, almost every anion, if I'm not mistaken, down the group the thermal stability increases. Okay. Now, regarding the solubility. So the first is for group 2 sulfates and carbonates. I'm not sure if they include nitrates as well or not, but for sulfates and carbonates, solubility down the group decreases. And the reason for this is mentioned in your A2. It has something to do with H-hide, H-sol, and H-lat. Don't get scared by this, it's a pretty simple answer, but it's something to do with in your A2 syllabus. So just remember that, for now, just remember that for group 2, sulfates and carbonates, the solubility down the group decreases. And for group 2, hydroxides, the solubility down the group increases. Okay, that's really all you have to remember for now. And the reason again is something to do with these three, and you'll learn more about this in your A2 chemistry. This is you don't need to go into an understanding of this now. You just need to know the fact for what it is. And I believe that is it for the group 2 lesson. If you do have any doubts, please leave them in the comment section below. And please, if you enjoyed the video and understood, please consider liking and subscribing.